and welcome to CERN from a quite crowded CERN control center, the nerve center of CERN's accelerator complex. Quite a big crowd of physicists, technologists and CERN staff is gathering today in front of screens in the LHC controls and the control rooms at the 4 LHC interaction points where the experiments control rooms are situated. We are here in spite of the early hour, today June the 3rd, 2015 in Geneva, to witness another important milestone in the LHC program. First stable beam collisions at an energy of 13 trillion electron volt. Commenting the milestone with me today is my co-host Steve Goldfarb. Hi, Steve.
Good morning, Paola Catapano. It's great to be here. The experiments are very excited. Today we're going to go to high energies and we're going to be entering a realm of exploration at 13 TeV. We have with us Mirko, Pojer, who is one of the engineers in charge who doesn't happen to be on shift today. And so he's going to walk us through all the different steps it takes for us to get to 13 TeV stable beams for physics data taking. Hello, Mirko.
Good morning, Steve. Good morning, Paola. So unfortunately, we were a bit late on the planning. We were supposed to really to be in the ramp, but we got some problem in the injectors and then in the LHC. So the present state, we have injected 3 nominal bunches that will be soon ramped up at the new record energy of 6.5 TeV. It's not a record for the energy we reach. We have already reached this energy in the past days, but today we'll declare for the first time the stable beams, which is the start of the physics, and the experiments could switch on their detectors.
So that's an important thing to underline. I would like to pick on that. You said we've already reached the energy breaking record of 13 TeV. So what's new today is stable beams. Why is this so important?
Yes, and in fact we have already as well done collisions at this new energy, but those were not collisions for the experiment to collect data. They were just collisions to set the reference point where we align the collimators around the beam. The collimators are let's say, the passive blocks that are put around the beam to close to the beam to protect the experiment from debris or deviation of the beam from the trajectory that could damage the experiment. So it is very, very important to set up the collimators precisely around the beam in the ideal trajectory, in the ideal trajectory of the collisions. That's why we had already collisions at the 6.5, but today, as I said, if the first time this year, the first time in history, we'll declare stable beams at 13 TeV center of mass.
And this is a historical first.
It's a historical first, and it's very, very important for the experiments because it means that we have now calibrated, aligned, gotten everything ready based on what we've seen so far from the LHC, and it means that now we can configure our experiments to all be ready to really take
And here they are.
data.
You can see them on the screens. We are in touch, and we will be going to speak to them very soon and quite a few times along this walk through the process of getting to stable beams at 13 TeV. We have the LHCb control room on the left top, and on the top right Atlas control room, and Alice on the bottom left, and CMS on the bottom right. We will talk to them very soon, but in the meantime, we could go to watch a clip that is gonna summarize for us what it takes to inject beams into the LHC up to ramping them and colliding them at 13 tera electron volts.
So welcome to the LHC RF zone. We are now in a surface building responsible for the acceleration of the particles in the LHC. About 110 meters underground, we have 16 accelerating cavities, and 8 for each of the 2 LHC beams. And each time the protons cross the cavity, they receive a little kick, which will, at the end, increase its energy to go to the top energy where physics would take place. The particles will cross these cavities 10,000 times per second. And the acceleration runs will last for about 20 minutes. So this means that it's a very, very, very large number of relatively small increase of energy to get to the collision energy. So right now, the accelerator is still empty, and we are waiting for the first particle to come from the injectors. So the injectors is a smaller accelerators, which will accelerate the particles to the injection energy, and thereafter will transfer them in transfer line in each of the two LHC rings. Right now we are just waiting for what we call a pilot. We cannot, for safety reasons, put a large a large number of particles in an empty machine because something may go wrong. So we want to take a little pilot or probe, if you want, which contains only a small number of particles to inject first and make sure that the machine is in good condition. And now the probe just came into beam 1. It may look large because it's 6,000 millions of protons, but it's still very small compared to what we call the nominal bunches. So now the injectors have sent one little pilot in ring 1, and we will wait for another coming pilot in ring 2. Thereafter, the operation will make sure that the global parameter of the machines are correct, and then they will go ahead to inject what we call the nominal beams. And depending on the number of particles and the distribution of the particles, which is just customized and requested by the operation. So you probably didn't hear it, but our LHC announcer just told us that we got pilot injected in ring 2. So now we have these two little bunches traveling very, very, very close to the speed of light, but not quite. Actually, if you were to put a fraction of the speed of light, right now they are at 0.59 followed by an 8 of the speed of light. So it's very, very close to the speed of light, but not yet. And during the acceleration run, we will still increase their energy, and they will get even closer to the speed of light, which for us, the RF is important because we need to remain at each crossing of our cavities, we need to give a synchronous kick to the beam. So we do see this very, very slight increase of the frequency to remain synchronous during the ramp. And we will see that later when the ring is full. So right now what they are doing is that they are changing the settings in the injectors so that the injector will prepare larger intensity bunches to fill with these so-called nominals. And see on the, so this is the, what we call the page 1, so with magnetic cycles and beam current. This is classic in all circular machine. The magnetic cycle will tell you what energy the machine is at, and the beam current will tell you how many protons you have there. So now they are changing this in the injectors so that we are ready for the injection of the first nominal in one of the two rings.
And we are back in the CERN Control Center on the 3rd of June 2015. We have here with us Philippe Baudrenghien, RF expert, that is radio frequency cavity expert. He was explaining to us in this clip how the whole process of injecting beams into the LHC and accelerating them happens. So, Philippe, the ramp has just started. Welcome. The ramp has just started. Where are we now with the beams, with the proton beams in the LHC?
So now we have these three bunches of each ring which are traveling at very close to the speed of light. They go 10,000 times per second around the 27-kilometer long ring. And in one place in the machine, there are a series of little gaps in the vacuum chamber where they get a little bit of energy increase. And this little energy increase at each turn is what will bring them up to the physics energy of 6.5 TeV. So
this place is where we saw you in the clip before.
The place is 100 meters underneath where I was in a surface building, and the place is in a big cavern located 100 meters underground.
It's 0.4 indeed.
This is 0.4, yes. So 0.5 is CMS, and this is 0.4 in HNV. And now, while we give this little bit of energy to the beam, it's, the machine is relatively delicate because you need to keep a good alignment between the magnetic fields and the energy of the particles. So this is what you see there on page 1, this little black trace is the magnetic fields. And as the energy increases, the magnetic field must increase as well, else the particle would be be brought outside of the vacuum chamber, and they would go
Right.
on what Mirko mentioned, these collimators, where
Yes.
you get the lost, the beam being lost. Now in the LHC, this acceleration process is very, very slow. You see, it takes about 20 minutes. During that time, the particle will go round trip, the equivalent of from here to Sun round trip.
So
it-
from injection energy, that is the injection energy of the SPS, to 6.5 TeV, it takes 20 minutes.
Yes, so injection energy
Okay.
is the extraction energy of the injector of the SPS, so the
Right.
450 GeV, and then so now we have already spent about 5 minutes. We are at 2 TeV, and it's going to take about 20 minutes to get to the top. So during these 20 minutes, there are lots of controls loops which have to fine adjust the magnetic fields so that the beam remains centers, and that have to adjust the RF frequencies so that we keep in track with the increasing velocity, slight increased velocity of the particles, so that by the time we get in physics, we have these bunch nicely packed together to optimize collision in the detectors.
That's very clear. Thank
Yeah,
you,
I
Philippe.
just did this quick calculation here. So these protons, you brought them in at the energy of the SPS. We use a variety. Actually, many people don't know that there's a variety of accelerators that are used to feed the LHC. We don't just start at the LHC. And one of those protons in these bunches is going to go around tens of millions of times before it gets up to energy.
Yes, so it will make 10,000 times per second, and this will last for 20 minutes, about 1,000 seconds. So this is, 10 millions of turns. It's by the time to get to 450 GeV to this 6.5 TeV.
So it has a lot of work to do.
Well, this is the beauty of circular machines. I mean, you can, slowly increase the energy in multiple paths through the same accelerator, while the parameters change. The magnetic field increases and the RF frequency changes slowly.
And you said we have 3 nominal bunches in there?
We have 3 per ring. So now we have to picture the machine as 2 relatively independent rings. The particles do not see each other. They travel in opposite direction. And by the time we'll get to the flat top after the squeeze, then they will be put in collision only in the 4 detectors. But right now they ignore each other, so they are separated, they call.
Very good. So I want to remind everyone that if you have questions to ask, please go to Twitter and use hashtag 13TEV, and you will have your questions answered, hopefully, because at the end of our session here today, we're going to be trying to answer questions. Okay, we're going to go live.
Okay,
to the
yes.
CCC.
So there is a traditional meeting every day. Of course, here operators work 24 hours a day in shifts of 3 shifts per day, and they meet traditionally every day at 8:30 to report about what happened during the night and to pass the baton to the next shift team and to decide what's the program for the day. So today we are not doing differently. There is going to be a meeting upstairs right above our heads here from the CERN control center, and there we are.
And we're going to see what
That's
they talk about.
the meeting is starting. That's Jan Uithoven. Jan is today reporting about what happened last night and what is going to happen today.
And we changed the cables. Then had a small wait for the SPS, had a problem on the beam dumping system. 7:30 the SPS was back, and we start to inject for physics, which is going on at the moment. So just to give an idea, basically before we want to go for stable beams, so normal physics collisions at 13 TeV, we want to be sure that the system is fully protected so we can't damage neither the machine nor the experiments. So this is a small part of a big list of all tests we need to do. So what was left and mandatory were the collimator setup and verification of the loss maps and the aperture. So that's what we did yesterday, the FMCM test and the interlock beam position monitors. So the collision aperture, that was measured at collision at 80 centimeters by opening all the collimators except the tertiary collimators around the experiments in 1 and 5. Then the beam had a gentle blow up, and one was observing the losses, and they should happen at the TCTs, but not at the quadrupoles, the triplets, which are protected. Then the TCTs were opened at steps of 0.5 sigma with a blow up, and this was repeated over several steps until the losses moved to the triplet. So from this, we get the aperture at collision for the two beams in the two planes. So basically this is around 15 to 16 and a bit of sigma, which is very close to what was expected and what was predicted from 2012. So basically with the settings of the collimators below this, so the 13.7 is well below the values we found, the triplet is sufficiently protected by the tertiary collimators, so we're okay to go with the settings we have in.
Pas maintenant.
So this is an example of the
Tu les
loss maps
prépares.
which were done. So the beam is being blown up, and then you check the losses and the losses you want to have at the tertiary collimators,
C'est
which
quoi
are
ces-
protecting the
what are
triplet
these
methods.
sounds?
So then there were more loss maps in the afternoon. So the betatron loss maps were made, they were validated, they were okay. Then the off-momentum loss maps in collision, they were done, but there were some question marks on it. And basically had some higher losses in IR3, about 10 times higher than we expected. So this can either be due to a novel method which we used of blowing up the beam with some RF expert tools which you can see here. So this consists of switching off the phase loop and injecting phase noise in the cavity. And you see that the bunch length is going up in time. And this saves us an additional ramp for the two off-momentum loss maps. So I want to do it with a classical method overnight, and this is what we did. Interlock BPMS test. So basically, there was one channel which was masked before. So this was being put back in operation. So we actually had to test it again. So we see you make a little bump on the orbit, and we found the interlock values, and this is okay. So at that moment, all the interlock BPMs were okay again, and the machine critical setting check was passed correctly. So we had this fast magnetic current change monitor test to be done. So basically, there was a whole list. So here you have the magnet circuits, which are protected by this FMCM interlock, which means if a magnet current would change, the beam is dumped, and you want to check that the beam is dumped before we have any problems with the orbit or significant beam losses. So this was done for all the missing circuits here at injection, and all the FMCMs triggered as expected, and no orbit deviations or losses were seen. And the one which are outstanding here at 6.5 TeV beam energy, they will be done as the end of field when we do the stable physics beam. In the end, we will do those tests. So then we also did the asynchronous beam dump test. So you can see how it goes. So this is where the beam is originally at the little diamond. We switch off the RF, so the beam starts to go around the machine. And this is where the abort gap is. And you see that the beam basically is going over the abort gap. And we can check the losses on the tertiary collimators and the TCDQ. And we look at the ratios. So the ratio was below 7.5 times 10 to the minus 4. That's okay. And also looking at the global BLM images, everything is fine. So the asynchronous beam dump was fine as well. So the plan. So yesterday we did our loss maps in the other machine protection test. At the moment we're going for the first stable beam. So we have injected the 3-on-3 nominal bunches. I'm looking there at the back on the screen. It's being ramped. It's almost up at 6.5 TeV. So everything looks good to go for the first physics fill at 13 TeV, beam collision energy. We want to go and do 3 fills. After the first fill, we go and change the polarity of Alice, as foreseen. And then tomorrow we'll do some more stable beams, some more physics at 13 TeV. And then we have to do a abort gap cleaning commissioning, and then we start to increase the number of bunches. And we hope over the weekend we'll be doing physics fills again at 13 TeV with 48 bunches. So now cross fingers and hope we get our first physics fill at 13 TeV. That's the plan. Questions, comments?
The status of the BPMS?
The status of the BPMS, so the one which failed, yeah, we rewind it to
Because
another.
people see this live.
So basically this is not the correct interlock, but it's redundant. So we're playing on the redundancy.
So that was Jan Oudhoven at the traditional 8:30 meeting setting the plan for the day. He just said we are going to go for stable beams at 13 TeV for the first time. We are back to the CERN control center now. Back to the commentators post here with Philippe Baudrenghien,
Hello.
who is helping up reading through what's happening on LHC page 1.
Well. Unfortunately, if I can believe page one, though, it seems that we lost the beam somewhere in the ramps around 40 eV or so. So we are keeping up with the ramp because there is no way you're going to stop the magnets. They need to ramp up to the top energy, but the bunches have been lost, meaning that they have been absorbed by this, Mirko mentioned, these collimators somewhere in the warm section of the machines, and that's completely secure for the machine, but unfortunately this is going to delay somewhat because so the magnetic field needs to ramp all the way with this empty machine to 6.5 TeV.
And then we have to go back.
And then we have to go back, but you know, these enormous superconducting magnets cannot be ramped down very fast. So this is going to be at least 1 hour or 2 hours before we are back into taking beam again.
Okay.
So depending on the faults, I don't know what happened. So the operator will now investigate and see how we can proceed. But
while we are on that, I think we can go to take a look at the experiments control rooms, starting with the Atlas control room. They're all gathered there, all the physicists from the collaborations, not all of them. Steve is not 3,000 people, wouldn't fit.
If 3,000 people, we can't fit them all into the control room, but we do get a good dozen or two in the control room. And those are physicists who are there to monitor the different components of the detector. While the LHC is probably the most complex machine ever made, one should note that these experiments are extraordinarily complex. They have around 100 million active channels each, and so they also require monitoring and checking. And all of the physicists who have their names on these publications actually take turns doing shifts.
Including the spokesperson.
Including the spokesperson. Frankly, I can say as a physicist, it's one of my favorite parts of the job, is to sit there and to monitor these beautiful, beautiful detectors. Maybe we'll get a chance to talk to some of my colleagues over there at Atlas to see what the environment is like. I think there's a lot of excitement today.
Yeah, the control rooms are more packed than usual. You can run the LHC with 2 people, I'm told. Is that right, Philippe? Here.
You mean here in the
Yeah.
well,
when everything is
the
nominal.
operators. Yeah, normally we at any time we have 2 operators running the machine. Yeah.
Yes, I see on the screen our first guest from the LHCb experiment on point 8 of the LHC. His name is Federico Alessio. He's the Deputy Run Coordinator. Hello, Federico, can you hear me?
Ciao, Paola. Can you hear me?
Yes, I can hear you.
Good. Thank you.
Okay. So, Federico, you are the first from the experiments to tell us what's the feeling today.
Well, we are very excited. We are all here. As you can see, the control room is buzzing with people. We were a little bit sad that we just lost beams, but we are confident that the machine will bring it back very quickly.
So you are Deputy Run Coordinator. Of course, in the LHCb control rooms, like in the other experiments control room, you have different roles, different people doing different things. What's the role of the Run Coordinator?
Well, in ACB we have 2 people. It's me and Patrick Rob, who is the run coordinator, and basically our role is somehow to organize the work that we have to do to prepare the experiment to take data, and then also to organize all the shift and all the people in the control room to take data, to be sure that we actually take data efficiently from the machine, from the collisions. This also means organizing the shift. As you can see behind us, we have 2 people on shift. In reality, you can see more, but at any time LHCb runs with 2 shifters, which are dedicated to take data and run the experiment for 24 hours over 24 hours.
Thank you, Federico. We'll come back to you during the morning.
Okay.
Of course, we cannot predict when we'll
Yes.
be ready. We are
Yes.
now moving to point 1, interaction point 1, where the Atlas experiment is situated. And I see Dave Charlton, the spokesperson of the Atlas experiment. Good morning, Dave. Thank you for being with us today.
Good morning.
So, what's the feeling at Atlas today?
Well, there's a lot of excitement, as you can perhaps see behind me in the control room, or at least there was until a few moments ago when the beams were lost. But we'll come back again, of course, soon and try again.
Yes, this is a special day for experiments. For the first time, you're going to see collisions, hopefully in less than a few hours.
Well, we've seen
with stable beams.
We've seen, with stable beams, precisely. That's really the difference today. Is it's the start of the production running of the accelerator. We've collected quite a few 13 TeV collisions already, but not with stable beams, so not with all of the detectors switched on. So that's the big step today.
It's the big step, and it's the official beginning of venturing into a new physics era. What is different at this scale, at the scale of 13 TeV? What's the difference with previously explored scales?
Well, because we're colliding together with higher energy, the protons, it means that we can probe to higher energies to produce higher mass particles and also to shorter distances than we've been able to before. So we're taking a step forward in the sensitivity to possible new physics.
So Dave, our colleagues were very, very busy the past couple years. What was going on at Atlas during the long shutdown?
Yes, so there's been a huge amount of work on the detector during the long shutdown, also a huge amount of work all around the world on the software and computing systems. The biggest single change inside Atlas has been that we have put in a new innermost pixel layer right at the center of the detector, which allows us to get closer to the interaction point to see particles very soon after the interactions, much closer in than we were able to before. So that's the big step for Atlas, but of course we've also changed many other things about the experiment. We can take data at higher rates than before, and various other improvements on the robustness and the performance of the experiment.
Thanks a lot, Dave. We wish you the best of luck for this new physics era.
Okay,
and
thank
we'll
you.
come back to Atlas soon. Now we are going to your friends at Point 5, CMS control room. And I see Tiziano Camporesi, the CMS spokesperson. Hello, Tiziano, and thanks for being with us today. So we were discussing about the start of a new physics era with Atlas. Of course, CMS is ready as well to venture into new terrain.
Absolutely, we are fibrillating here.
Really? So the control room is more crowded than usual as well today?
Well, I would say full to capacity.
Yes.
We are actually sending people out.
And CMS as well is for the first time all fully ready to take data now, for the first time at 13 TeV with stable beams.
Yes, exactly. We have already taken data while the machine was tuning up the beams, but this is really the time when we start the physics program.
And how long will this program last, the 13 TeV program?
Well, it's going to be for the next 3 years, because basically this is the way the machine is scheduled to run. Is having several years of running interleaved by extended periods of maintenance and consolidation.
So if I can ask also...
It is really the beginning of a long run.
I would like to ask you the same question I asked of Atlas. I'm sure CMS had a lot of work that they were doing during the long shutdown. What types of things changed with CMS in preparation for the high energies?
Sorry, I lost the audio. Can you repeat, please?
Okay, sure. My question was simply what kind of work went on over the past couple years during the long shutdown on CMS? I'm sure you guys were very busy doing work.
Absolutely. We, in fact, took the occasion of this 2-year stop for basically finishing the detector which we wanted to have from the very beginning. We didn't have the resources at the time for being able to do it, and so we basically have completed the detector which we had designed to start with. So there was a lot of work, and in fact there's been a lot of work in preparation for this run, because we have basically renewed all of our data acquisition system. We have new detectors, we have all new software, much more efficient than we had in the past, and so we have been basically working to prepare this startup flat out over the next 2 years, and in fact we have been effectively running, emulating running at the LHC for the last 6 to 8 weeks.
So we wish you a lot of pleasure with the new collisions, Tiziano.
Yes.
Thank you, CMS. So we're going to move now to the Alice
Ciao,
control room,
Paola.
where I see Paolo Giubellino, the Alice spokesperson. Hi, Paolo. Can you hear us?
Loud and clear.
Perfect. So,
Hello, Paola.
hello, and thank you for being with us. The Alice control room is also full of people today.
Yeah, it's extremely
Can you feel the
crowded.
atmosphere? Can you feel
Definitely.
it's special compared to the other days?
Yeah, because you can imagine. I mean, this is the reward for years of hard work. I mean, people have been preparing for this for more than 2 years. We've done really major changes. Starting with this room where we are, which is completely new. I mean, it's the first time it sees beams, and going all the way to having installed the new detectors, having completely changed our data acquisition and online systems, and so on and so forth. So it's also really a test of the quality of all the work we have been doing. So there's very many people which are, very eager to see that what they've done through these 2 years really comes to work and sees particles. So this is a great moment.
So Alice will be, you've made some very important measurements in run 1. You have some high expectations for run 2?
Absolutely, because you can imagine we have learned a lot through run 1. So Alice, like the other experiments, has been able now to focus much better on what were the best ways to approach the data. So not only we will have a new machine which gives us twice the energy and much higher luminosities and so on, but also we have been able to retune all of our instruments and add more in order to get really the best physics out of this. There were several hints of really new things coming up in the measurements of run 1, and so we have prepared to now focus our activity just on those. And so this is a really great moment for physics.
Thank you, Paolo. We'll come back to the Alice control room very soon and a few times during the day. We now move back to the CERN control center where the director for accelerators, Philippe Baudrenghien, is ready for his opening statement today.
Okay, now we are just preparing for the physics operation, stable beams. We had the first tentative, and during the ramp at around 4 teraelectronvolt, we lost the beam due to certainly a timing problem. Now we are looking at these things. There was a synchronization of the timing. If something happens during the operation, we have to look at, to investigate, and I think in a while we will recycle the machine to inject 3 bunch against 3 bunch and to restart the ramp squeeze and declaring stable beams. Then it is a part of the operation. Thank you.
And that was Philippe Baudrenghien, director for accelerators, explaining where we are now. It's normal, Philippe, to lose the beam. The LHC is a prototype, is an experimental machine, and these things happen. You just don't switch a button and everything goes fine. It's quite a complex operation.
Well, hopefully, I mean, once we run in smooth physics, these happen less often. But no, the machine was restarted in April after 2 years of long shutdown. I mean, where we stopped the machine to accommodate for operation at higher energy. And sure, some of the systems have to be recommissioned. So systems like the timing and interlocks and so on, I mean, these are always delicate. That asks a phase of commissioning. So I don't know exactly what happened, but these ramps that get aborted are not exceptional in this restart of the machine phase.
We are now in the ramp, as you saw, starting. We have these 2 nominal in each ring, so that once we get to the flat top, we will have this collision in the 4 experiments. Right now, there is absolutely no collision. The 2 beams, as you may know, in the LHC, they are in different vacuum chamber, and they would see each other only in the detector. But until we get into physics, in the detectors, the trajectory of the 2 orbits is carefully adjusted so they don't see each other. We say that we have the separation on. During the ramp, we have to increase slightly the energy of these particles, but it is very, very small. As I mentioned earlier, we have 20 seconds, and per seconds they will cross 10,000 times all cavities. So at each crossing, we give them only a very, very small energy. And this energy accumulating over the full ramps will increase their energy from the injection 450 GeV to the 6.5 TeV that they need to have in physics. So two things are important for the RF during the acceleration. One is to stay synchronous so that we compensate exactly for the little increase in speed of these particles getting closer and closer to the speed of light. And this implies that we have to change the frequency very little as well during the ramp. And we will have a look at this energy increasing shortly. The second thing we have to do is to make sure that the band shape remains the same as it was at injection. It's what we call the emittance blow-up. So if we don't do anything, the nice little bunch that you see there would shrink. The size would become very, very, very short as the energy increase. This is just a pure natural process, which we call adiabatic damping. And this would be unacceptable because the bunch would be so short that they would not be stable in the machine. So during the acceleration ramp, to compensate for this natural shrinking, we gently shake the bunch. So it's like having a pile of sands on the table, and you have to gently shake the table to make sure that the size of the piles remains constant while there is this adiabatic shrinking.
And that was Philippe Baudrenghien a few days ago during one of these cycles of the machine. So you were explaining the ramp, and this is what we would like to see now, ramping the beam. We are ramping down at the moment.
Yes, so as the magnet were ramped up to the 6.5 TeV, equivalent magnetic fields, now we have to be to go down very slowly to the injection energy 450 GeV. Now the reason why you have to go slowly is because in this big magnets, you have these superconducting windings, which, although they have no resistance, if you want to change their voltage, you need a lot of current. I mean, this is in electrical engineering called inductance. So you have this enormous inductance, which implies that the ramping is relatively slow. So it takes about, I think it's between 30 and 40 minutes to ramp down to the injection energy 450 GeV. Then we will again synchronize with the injectors and refill the machine.
So these magnets are very special. They're made out of material called niobium titanium, which we have when we cool down to 1.9 degrees Kelvin.
Sorry,
we cool it down to something like 1.9 degrees Kelvin to be able to have them operate as superconducting magnets. They're at a very, very low temperature. And so that makes them different than any other collider that we've ever seen. So now we're going to talk with some other people at the CCC. At the moment, we're waiting to see what the situation is for the magnets and the collider.
It's 449.
And okay, we don't yet have anything going up. We're actually ramping down the magnets, which is something that Philippe just explained. You have to do slowly and carefully, and take some time.
And somebody's investigating. What does it mean, Philippe? They're investigating.
Well, so the engineer in charge. So in the LHC we have an operation team. So of course today it's a bit exceptional. So there are many persons, but there is always an engineer in charge and a technician. And the engineer in charge is responsible for the machine operation during his shift. And I guess now, as we had the first news that there was apparently a timing problem, they are trying to see what happened that decided to dump the beam in the middle of the ramp. Now, I have not much additional news yet, okay, so.
Well, when we ramp back up, it's going to be very interesting. The various experiments that we've spoken with. There are a variety of them on the LHC, not all of them the same. I think it's interesting to note that you have the two large experiments, Atlas and CMS, which have 3,000 to 4,000 collaboration members each, working to be able to do general purpose physics, that is exploring. And we also talked to LHCb, who is trying to answer some very, very important questions, one of them being the antimatter in the universe, what happened to it, and the Alice experiment, who we talked to last, where we were finding out where their primary goal is to look at the universe in its form before protons and neutrons were formed, when quarks and gluons were traveling freely. It's very early in the lifetime of the universe. And all of the experiments are keen to get the data that's going to be coming this year at the high energy.
And here we're seeing an animation showing exactly where the 4 LHC experiments are situated at the crossing points where the bunches interact, the proton beams collide. We will see now very soon zooming in on the 4 points where the experiments are situated. You can see Alice at point 2, Atlas at point 1, LHCb at point 8, and CMS at point 5. And the beam is starting its circuit in the clockwise direction from point 2 and the anti-clockwise direction from point 8. So Alice and LHCb are basically the first experiments to see beam, and Atlas is the last one.
Yes. We don't really take it this way, frankly, but yes. The reason why we put these 3 bunches here is that we want to accommodate for some collision in all 4 experiments. Now, this is very, as you see in the animation there, we just have a little bunches. I mean, this few bunch, which is not unlike what we do today. When we really will be operating in good physics, they will be up to 2,808 bunches in the ring. That is about 1 bunch every 25 nanoseconds or every 7.5 meters, so following each other by 7.5 meters.
So these bunches, when we talk about a bunch, you might think, oh, a bunch of grapes, you have a dozen or so.
Right.
How many protons are in one of these bunches? I think quite a few.
The nominal bunches, we put 10 to the 11. So 10 to the 11 is 100,000 millions of protons. And we pack them, so we hopefully will pack them every 7.5 meter. So all in all, the machine will have about 1/2 amp of DC current. So I mean, the total current in the machine will be 1/2 ampere. Now, but in 2012, we put more particle per bunches, but we had way fewer bunches. So we would put the bunches 15 meter apart, that is 50 nanoseconds, but we went up to about 40% higher than these 10 to the 11 that we now want to operate with in 2015 and following. And the collision energy, of course, was lower. We collided with 4 TeV per beam, that is 8 TeV collision energy.
We are going now to the experiments again, because we were a bit in a hurry before, and we would like to ask a few more questions about what these detectors look like. In the end, it's their day today. I can see Rebecca Suarez-Gonzalez at the CMS control room. Rebecca, hello. Can you hear us? Rebecca, we see you, but I don't hear you.
Could be the same for her.
Yes, I think she doesn't hear us. Rebecca, hello?
Hello, can you hear me?
Yes. Okay, that's great. Hi, Rebecca, welcome.
Hi. Thank
you. So
you.
while we're waiting for beams to be re-injected in the LHC, we thought it would be a good idea to discuss a bit about the detectors, the CMS detectors. It's okay. What is special about CMS? Tell us how it works and.
Well, what is special about CMS is that it's compact. We have a very big solenoid magnet. That is the largest solenoid magnet that has ever been built. That usually operates at 4 Tesla. And due to having this very big magnet, we can have a very strong magnetic field within the experiment, and that allows us to have most of the subdetectors inside the magnet. Like this, we can be a bit smaller than Atlas, for example, but what happens is that, on the other hand, we are much heavier.
So this is Steve here. I have some questions coming from across the ring. There's a whole lot of things that we all want to look for in the coming years. Do you have a favorite topic of physics that you think is something that could happen in the coming years with this higher energy?
Sorry? So I do have favorite physics topics for the next runs. In particular, I like new physics that involve top quarks and Higgs bosons. I think they're very interesting, the interplay between these two particles, because the top quark is the heaviest quark that we have found so far, and it has a very strong relationship with the Higgs and with stability of the universe. So there are a lot of models of new physics that involves top quarks or top partners that I think they are particularly interesting, because these kind of things give nice signatures experimental that are very fun to study, and they could be a window to many different theories beyond the standard model.
Well, yeah, I think that's a very important point. It's very interesting physics. Many people don't really understand that the Higgs boson, finding it was only our first step. And now exploring it like you would like to do, looking at its interactions with the top quark, for example, measuring all of its properties, might be our way to find what's beyond this beautiful standard model we have.
Yes, I agree.
Yeah. I say beautiful, but
Yes.
in a sense, many of us would really like to break that standard model and to find out what else there
Right,
is
and
out
you
there.
say beautiful, rightly so, because we're going to say hello, bye-bye to Rebecca now, and we come back to CMS soon. We're going to move to point 8 of the LHC, where Guy Wilkinson, the spokesperson for LHCb, is ready to talk to us. Hello, Guy.
Oh, I hear you.
You can hear us well?
Yes, you hear me?
Okay. I hear you a bit not loud enough.
Your volume's a little bit low.
I'll get our people to work on that. The volume's
Yes,
a little
but
low.
it's understandable.
Okay.
So we were talking about beauty. What about beauty at LHCb?
Indeed. Our experiment is studying beauty quarks. Our goal is to make very, very precise measurements, and what we are trying to do is understand the difference in behavior between matter and antimatter. And a very good way to do this is to make precise measurements of the decays of beauty quarks.
So you're answering a very profound question, or at least you're hoping to answer a very profound question, which is why are we here? Why didn't we annihilate with antimatter in the early universe?
Exactly. In the early universe, matter and antimatter were produced together in equal amounts, and now we seem to have matter. We only seem to have matter, and this tells us that matter and antimatter behave in slightly different ways, and this is the purpose of our experiment, to learn more about this.
And the B quark is especially important for this?
The B quark is an ideal laboratory for these studies. In the B quark, there are many CP violating effects, that is matter antimatter violating effects, which are very well predicted in our theory of particle physics, the standard model. So our purpose is to make very precise measurements to try and compare those measurements to the predictions of the standard model. The standard model cannot explain this imbalance between matter and antimatter at the level we have it in the universe, so we know there should be something else out there which is driving this, and therefore we hope to see discrepancies in our measurements.
Mm-hmm. Is there a big difference between what you can find in the standard model and what we actually measure?
Enormous. The standard model is many orders of magnitude away from being able to explain the imbalance which does exist in the universe. So there should be a very clear signal. There are many ways to look at it, but certainly our measurement program is one of the most promising.
Guy, during the first run, LHCb performed wonderfully. You published a lot of papers. You made a lot of fantastic measurements. How is 13TV going to make a difference?
For us, the increase in energy is not the main benefit. The main benefit is the fact that we're going to collect a much larger data sample, and our detector is more ready and able to take advantage of this large data sample, and we will be able to increase the precision of our measurements. For LHCb, precision is all, and the bigger data sample that run2 will bring is very exciting from that point of view.
Thanks a lot, Guy. We're going to leave LHCb now and move on to the ALICE experiment at point 2 of the LHC. Hello, Alice.
Hello, can
Hi.
you hear us?
Yes, we can hear you. I don't have your name. Can you say your name, please?
Hannes Wessels.
Hi, Hannes. And what is your role in the ALICE experiment?
I'm one of the deputies.
One of the deputy spokesperson, okay. So before, when we were talking to your spokesperson, we didn't dwell too much on the detector itself. We would like to know more about ALICE. We see in the banner behind you, it's called a Large Ion Collider Experiment. So you collide ions.
If the machine lets us, yes.
Yes,
so we are gearing up
will.
with the exactly. So our prime time will be in November, and we're gearing up with the proton beams now, and actually perform important reference measurements for our measurements to come in November.
So in a sense, this is Steve. In a sense, you use the proton collisions to set certain levels that you can understand or calibrate your detector?
Well, no, actually, it's really physics motivated. So what we want to do if we collide ions, we want to really study what happens if you have large lumps of quarks and gluons mashed. And these properties you can only understand if you understand what happens in elementary PP collisions. So everything that we study when we collide heavy ions, we compare to what is happening if we have a very small system. So we can study the transport properties, how it expands, how it behaves. And this is really the goal of our investigations.
Mm-hmm. And now, given the measurements that were made, you made some very important measurements during run 1. Are there specific goals that you have in mind for run 2?
Absolutely. So, I mean, with the increase in energy and the increase in luminosity, so we will have much more data. At the same time, you've heard that we've actually used the shutdown to consolidate the detector to be able to take twice as much rate. And through this, we will be able to be what we call much more differential in our observations, really study specifically the transport properties of the matter.
That sounds fascinating. You're really looking, well, many people describe this as looking at the very early universe. You're seeing the properties of quarks and gluons before formation of protons and neutrons.
Exactly. And how this actually expands into the vacuum.
Mm-hmm. Excellent.
Thank you, Hannes. We're now moving on to point 1 of the LHC with Alex Cherry. Ciao, Alessandro.
Ciao,
Hi.
buongiorno. Good morning.
Good morning. So before we didn't speak a lot about Atlas. Atlas is the largest of the 4 LHC detectors. Can you tell us more about this fabulous experiment?
Indeed, it's an impressive, large experiment. If you have a chance of visiting, if you've had the chance of visiting it while we were in shutdown, it's 25 by 25 by 45 meters. It's the largest of the experiments. It's a huge cathedral of particle physics, basically, and it's one of the 2 general-purpose experiments at the LHC together with CMS, which basically means that we look at collisions, looking for several different phenomena, among which, as you know, the Higgs boson that we discovered.
Exactly. I was about to mention, we didn't mention yet, but we should say that this was an enormous discovery.
I happen to be on Atlas, but I'm trying to be neutral here.
It was an enormous discovery, and did you expect it to find it at 7 TeV?
Well, we worked hard to find it. Of course, you know, the nice thing about these kind of experiments is that you are really at the forefront, so you can never be sure what to expect. We had hints that possibly in certain models, the Higgs boson could be there and could be already found at these energies. But,
and now one wonders, what's next? Why bothering going higher in energy? You have the Higgs, you have the standard model, it's complete. What's next?
It's complete, but we know it's flawed. And we know that there is something else to discover. The question is whether and how much we can discover with with this next run. The discovery potential is going to be very, very large. We do expect that something could possibly be found in the near future, but no matter whether we find something or not, this is going to be an important piece of information in the puzzle of building a more complete model than the standard model itself.
That's what makes it so exciting to go to 13 TeV now. We are jumping by almost twice the order of magnitude in energy.
Yeah, I think Alex made important points there. That the Higgs boson now, as we discussed, is discovery is one thing. Now we have a tool, right, to explore with. I think that's something that certainly Atlas and CMS will be focusing on in the coming years.
Definitely, it's going to be important to refine and understand more about the properties of this new particle, and it's going to give us hints on what could possibly be beyond as well.
Because we have still some very big questions, as you alluded to. The standard model is wonderful. It's somewhat complete, but there's so many big questions out there. And one thing that has been brought up by many people are curious about is this thing that we refer to as dark matter. Is Atlas going to be able to look for dark matter?
Well, we know that dark matter is there from observing the cosmos. If we discover new particles, then some of these new particles may be responsible for accounting for this dark matter. So in this respect, we could be able to give at least a part of the answer to what dark matter is made of.
It's quite a special situation, though, that you before you had hints from a theory. The Higgs theory was extremely precise, and it was a good hint. It didn't tell which energy you would find the particle, but it had to be there. Everybody was convinced. Now you have cosmology telling you that there is something beyond the standard model, and that's dark matter. Mm-hmm. So it's quite a special situation that makes. Does it make you feel closer to astrophysics and cosmology?
Well, cosmology and particle physics are getting closer and closer as they become more and more scrupulous in understanding how the universe works. And yeah, it's definitely exciting. And it's something that we've seen growing in the last 10, 15 years. So definitely, yes, there is a lot of exchange at this point. And the LHC what's exciting is actually that it is the kind of machine that allows you to explore new physics in a very broad spectrum. Is what we call a discovery machine rather than something that allows you to measure precisely properties of particles that you know are already there.
So, Alessandro, thank you very much for being with us. We'll come back to Atlas soon. We now would like to take a look at these detectors. We've been talking about Atlas, CMS, ALICE, and LHCb, and we have never seen so far how they look like. So we're going to do that in the next clip.
That was Alex.
Okay. Oui.
And we're back to the CCC. We've just seen a very short sequence of the 4 LHC experiments during the long shutdown one, accelerated a bit. Mm-hmm. So we are now, we would like to remind that there is Twitter
Oh yes, absolutely.
Right.
It's very important. We are really ready to answer questions. We've already made attempts. In fact, last week we had a very popular Ask Me Anything on Reddit, where physicists from the experiments and from the accelerator answered various questions about what's going to happen in the coming years. And we're going to have some of the top physicists from the laboratory here at the CCC. And so if you want to ask a question, please use Twitter and use hashtag 13TEV, 13TEV, and we will try to answer your questions. That will be happening later on. We actually have some we're monitoring online here. I don't know if I can read fast enough. The tweets are coming in. Quantum C30 is following the physics at 13 TeV from the Canadian Light Source Control Room. So we have fellow physicists who
following
are
us. I know
tuning
they're
in.
following us from the States. I know Fermilab has organized
Fermilab's on.
a coverage of this event today.
And so we will be trying to answer questions. So again, please tweet your questions. We already have a fairly large list, but we're always happy to hear more about what the physics is going to come, because there's a lot of excitement here. The physicists are excited because, well, we don't know what will happen. Paula, actually, one thing that's important to note in exploration as we go to higher energy is that there's a very, very good chance that it will take quite some time. The next year or two could be done doing precision measurements, which is really how physics explores. We do precision measurements. We measure our current understanding the best we can, and eventually, with a high enough precision, we might see where things deviate, where measurements change. So excitement doesn't always come like the Higgs boson.
Right. And these things take time, including what happened today. We lost the beam, and now we are trying to, the operators are trying to refill the LHC. This can take a lot of time because we started the ramp and we had to complete the ramp, bring in the magnets, magnetic field to 6, and so it's gonna take some time.
Yeah, and I think our terminology, what we're used to talking about here at CERN, might not be familiar with the world. When we say lost the beam, it simply means that we dumped the beam in a controlled dump because the conditions were not perfect. The conditions for the LHC to go around and to make collisions have to really be perfect to ensure the integrity, the safety of all of the equipment that we have underground. We have beautiful, beautiful experiments. And so when any bit of precision is lost, if the timing is not perfect, then we dump, there's a controlled dump of the beam, and that's called losing the beam. We know where it is.
Yes, and so waiting for the beam to come back, we are going to suspend the live coverage for 30 minutes. We're going to come back in 30 minutes' time with more news from the CERN Control Center.
Okay, so we can all get our cups of coffee this
Right.
morning, and then we'll be back here.
And good luck, LHC.
Yes.